This is chapter 21, video assignment 1. The question states, a dang old rock was found to contain 5.51 milligrams of uranium-238 and 1.63 milligrams of lead-206. Determine the age of the dang old rock. So step A, assume all the lead-206 came from uranium-238 decay. 0.01 moles of lead-206 weighs 206 milligrams, and 0.01 moles of uranium-238 weighs 238 milligrams. Done, right? How much did the 1.6 milligrams of lead-206 weigh when it was uranium-238? So to do part A, we're given that we have 1.63 milligrams of lead-206, which has decayed from the uranium-238. So we need to just take that to moles so we can take it back to what the uranium once was. Excuse me. So we have 1.63 milligrams of lead, and it's given to us that 1 millimole of lead is 206 milligrams, right? That's just the atomic weight there. So when we multiply the milligrams of lead that we have times the atomic weight, we find out 0.00799126 millimoles of atoms, right, of lead. And since we have that many moles of lead, originally there were that many moles of uranium. So we can times that value by the atomic weight of uranium-238, which is 238 milligrams per 1 millimole. So that gives us 1.88 milligrams of uranium. So originally, instead of there being 1.63 milligrams of lead, there's 1.88 milligrams of uranium. The difference there is obviously just because all the top particles and stuff flew off. So step B says, what was the total mass of uranium-238 originally in the rock? So to find that, we can just sum the current mass of uranium-238 with the value that we just found was there, or the value that has been turned into lead. If we sum those two values, we'll have the original value. So 5.51 milligrams plus 1.88 milligrams equals 7.39 milligrams of uranium were originally there in the rock. Step C says, given the half-life of uranium-238, what is the rate constant K of the nuclear decay in units of year to the minus 1? I guess I use lambda, but K, same thing. So the rate constant is equal to the natural log of 2 divided by the half-life. So the half-life in the appendix is 4.47 times 10 to the 9th years, which is a long time. So natural log divided by that is 1.55 times 10 to the minus 10 years to the minus 1 per year, one every year. So that's step C. Now step D, finally, is how old is the dang old rock? So taking all the values that we've found out, we can plug them into the half-life equation. So T as time, age of the rock, is equal to negative the inverse of the rate constant, 1 over 1.55 times 10 to the minus 10, times the natural log of, normally this is n, like number of nuclides, number of atoms, but the ratio of masses is going to be the same for the original mass of uranium and the current mass of uranium, so we can just use mass here. So anyways, the inverse of the rate constant times the natural log of 5.51 milligrams currently, divided by 7.939 milligrams originally, which gives us a value of 1.89 times 10 to the 9th years, or in other words, 1.89 billion years old. So it's a pretty dang old rock.